Hello everyone, welcome to chapter 11, and in this section we are going to talk about the third state of matter that we introduced previously in the course, that state of matter being gases. So usually when I begin this chapter, I talk about this very famous or infamous football game that happened in January, I believe it's 2015, that involved the Patriots. And why am I talking about football in a chapter of gases? Talking about it because the ideal gas law, a statement that we're going to talk about later in this chapter, was often used when talking about this football game that involved the Patriots with regards to something called Deflategate. So if you remember this football game that involved the Patriots, it turned out that the footballs that they were using were not inflated to the proper pressure, and therefore people were saying that the Patriots had been cheating in the game. There were some people that said that the pressure in those footballs was too low, that gives them an advantage. Then there were others that said no, the reason why the pressure in those footballs is too low was due to the ideal gas law. We'll talk about what the ideal gas law is, as I said, later. But generally, in a normal semester, I would start my lecture on this chapter talking about this famous football game, because it is one way that the property of gases was talked about in society at that time. But I think what's probably more realistic, or not realistic, more apropos at this time is to think about gases in terms of their properties in a biological aspect, particularly with COVID-19 going on, and the importance of respiratory therapy that we see with doctors and nurses now. The mechanism for how our lungs work and how gases fill our lungs and get released from our lungs, all of that can be explained via certain gas laws that we will talk about. So I'm going to refer both to this football game and to respiratory therapy frequently throughout this chapter to illustrate some of the properties of gases and the mathematical equations that dictate their behavior. But let's talk about just some very general properties of gases, things that come to mind when you think about a gas. So when you think about a gas, you think about something that is easily compressible. It's a lot easier to compress air than it is to compress a solid, right? Gases, they assume the shape and volume of their containers, be it a volumetric flask or a person's lungs. Gases generally are very low in density in comparison with liquids and solids. And one of the reasons why that is because their behavior is explained by something that's called the kinetic molecular theory. You will actually visualize this in a simulation on the online lab for gas laws that you will do. And we'll talk more about the kinetic molecular theory when we get to the ideal gas law portion of this chapter. But basically, this kinetic molecular theory just states that gases, a gaseous sample that contains particles or molecules that are in constant motion, and when those molecules are in motion, that speed increases with increasing temperature. When you heat up a sample of gas, those molecules are going to move around more. And those molecules, when they are moving around, they interact with the sides of the walls of their container, thereby producing a pressure. The interactions that gas molecules have with each other are negligible or small in comparison to the interactions that they have with the sides of the walls of the flask. So what I just said verbally about the kinetic molecular theory, you can kind of see in this figure on the right, which we've got these gas molecules moving around. You can envision that they're going to move around faster if you apply heat to that sample. And those gas molecules hit the sides of the walls of their container. And when they produce that force, when they hit the sides of the walls of that container per unit area, those molecules exhibit a pressure. Pressure is one way that we can describe a gas's behavior. So when we talk about pressure, there are a variety of different units that exist to explain or quantitate the pressure of a gas. I'm sure you have heard of PSI before, pounds per square inch. This table here on the left just lists different units. The ones that are going to be the most commonly used in this chapter are going to be the ones that I have, say, memorized here, but obviously you'll be able to use your notes on quizzes and exams. The standard international unit for pressure is ATM, atmospheres. But the three units that we're going to use most frequently in this class are atmospheres, get my pen here, atmospheres, torr, and millimeters of mercury. And what's nice is that you can convert between those units of pressures using those two conversion factors. Okay? So, for example, let's say you're doing a calculation and you know what the pressure is inside the little air sacs in an individual's lungs. Let's say you know the pressure inside that patient's lungs is 757 millimeters of mercury. You want to know what that pressure is in two different units, torr and atmosphere. And so to do that problem, you would set it up as you would any other conversion problem, write down what you're given, use the conversion unit that's going to assist you. So in this case, I'm going to torrs. So I need to write down that 1 millimeter of mercury is equal to 1 torr. And I write that, so my millimeter of mercury unit cancels and I'm left with torr. Then I can do something similar when converting that pressure in atmospheres, but in this case using the conversion unit, 1 atmosphere is equal to 760 millimeters of mercury. Again, writing that conversion units, the units cancel, and I'm left with atmospheres. So from this little beginning video, you should know those three properties of the gases, know the kinetic molecular theory, and be able to convert pressure readings between atmospheres, torr, and millimeters of mercury.